Good morning, everybody. Welcome to Monday morning at Chem 11:05 with your host, me, Dr. White. Hi, everybody. Hi, some important announcements. First of all, over the weekend, I caught up with all the labs. You should see on Blackboard your score for a lab if you handed it in. Now, a couple of you, I couldn't open up the PDF file, and I sent an email for you to redo it. In other words, upload a PDF file that I can open up so I can grade it. All right. Another thing, I made a slight change in the syllabus and the lab part. I moved one lab to this week with another lab, and we'll talk about that tomorrow. Sometime later today or tomorrow, I'll modify and upload the new syllabus. Now, some advice from the management, me. Coming up soon after spring break will be test 2. Test 2 historically has the lowest average of the whole semester. I like my fancy hand signals. But anyways, study. Do the practice problems now. On Wednesday, I'll do the practice problems for chapter 4. I gotta get that fixed. And make sure you do them. Also, I will I highly recommend you do the practice problems for balanced chemical equation. And you do the practice problems for chapter 5, which we'll do after the break. All right, let's get to work. Now, last week, I talked about the mole. Remember, a mole is the chemist's counting unit. And we were talking about the different ways or definitions of what a mole is. 1 mole of an element is Avogadro's number times 6.02 times 10 to the 23rd atoms of that element. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. 1 mole of an element now equals the atomic weight of that element in grams, and 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights. And unlike in the past, long ago, I've cut down the memorization for this class, so this will be given to you, but you have to know how to use it. And we're doing some practice. I'd like to do some more practice, but first, I better open up a periodic table because we'll need it. All right, let's do the following. I'm going to start writing again. I still have to remember, don't use cursive print. All right, let's look at the following problem and notice 8 points. how many moles sodium chloride, NaCl, remember that's table salt, are 1.378 times 10 to the third grams of sodium chloride. So what do you do first? What are we being asked to find? Next, what are we given? So this is what we have. This is the only number we have to work with. Now, what units do I want my answer in? Well, we took the time to figure out that's moles. Oops, almost did it again. It's want to draw right cursive Monday. So this is what we want to get to. If we had a ratio, what would go on top and bottom of that ratio? And how do you figure that out? It's time to use your good buddy, your good friend, unit analysis. And it has been mine for many decades. Sorry, I shouldn't have said that, but it has been. All right, how do you use unit analysis? Whatever units you're trying to get to goes on top of the ratio. Whatever units you're trying to get rid of goes underneath. And now write those units. So I want some ratio, moles of NaCl to grams of NaCl. Where do I have a relationship? Grams of a compound to moles of a compound. Well, if you look at important information, test number 2, 1 mole of a compound equals the molecular weight of that compound in grams. The molecular weight of that compound, by the way, is the sum of all atomic weights. So, therefore, what I need here is 1 mole, and here, this is the molecular weight of sodium chloride. MW is shorthand for molecular weight, and we want the molecular weight of sodium chloride. Well, the molecular weight is the sum of all atomic weights in that molecule. There's 1 sodium, 1 chlorine. Now, where do we find those? You go to your favorite neighborhood, friendly neighborhood periodic table, sodium. Remember, on test 2, it will say underneath your name, please use proper significant figures for all calculated answers. On test 2, it will also say, please use three significant figures for all atomic weights. So sodium is 22.989. The 3 significant figures, that's, you're right, 23.0. Chlorine is 35.453. It's over there. Can you see it? And the 3 significant figures, that's 35.5. So there's 1 sodium, 1 chlorine, add them together. Remember, this is the sum of the molecular weight equal what 1 mole in grams is. Now, when you add, you get the same number of significant figures to the right of the decimal that the numbers you're adding that has the fewest significant figures to the right of the decimal. This is 1, this is 1. Oh, this has 1, so I can use it. Now, before I pick up my calculator, I'm going to check my units. What do I mean by that? Notice this is grams of sodium chloride times moles of sodium chloride divided by grams of sodium chloride. That's what this equation above is. So anything divided by itself equals the number 1, cancels out. This cancels out, this cancels out. I'm left, yay, with the right units. So this cancels out, this cancels out. I can pick up my calculator. I will. Turn it on, clear it. .378, blue key double E to get the exponential. 3 times, or whoops, not times, divided by 58.5. Oh, wow. My calculator gives me this answer. And let me make a little room here. And if you wrote this answer down, I take off a point, because when you multiply and divide, you get the same number of significant figures as the number you're multiplying, dividing by, as the number that has the fewest significant figures that you're multiplying, dividing by. How many significant figures in this number? 1, 2, 3, 4. All non-zero numbers are significant. How many in this number? 1, 2, 3. 1 is part of the definition or to define, so that's the exact number not involved in the determination of significant figures. So which is lower, 3 or 4? And time's up. Hopefully I'll pick 3. So to round this off, the 3 significant figures, keep the 2, keep the 3, keep the 5. Those are my 3 significant figures. Use the next number, the 5, to round off. That's 5 or higher. Delete all this, increase this by 1. And the correct answer is this. And you could have also written this. You wanted to do it in decimal. And let's go through this again. What did we do? We found out, first of all, what are we being asked to find? Moles of sodium chloride. We write down or find out what are we given? And that's grams of sodium chloride. This is the only number we can start with. This is what we're trying to get to. And you use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever we're trying to get rid of, units, go underneath. And where do we get a relationship of moles of a compound to grams of a compound? From important information, test number 2. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound equals the sum of all atomic weights. And let me just remind you, when you have one thing equal another, there are two ratios you can form, one side over the other, and the opposite, the other side over the other, which is how we fill that in. 1 mole per 58.5 grams. And that's how you do it. You know, something that was fun. Let's do another one. All right, 8 points. How many grams H2S? That's hydrogen sulfide. That's the stinky stuff you smell from an egg. If you open up a hard-boiled egg, oh, it doesn't smell well. Well, I like them, but my older sister hates them with a passion. Oh, does she hate making hard-boiled eggs? Certain recipes she has to, and usually I go over and help her and do that. Because, oh, she hates the smell of that. And if you've ever been to a forest preserve, I haven't been to one in years, come to think of it, but you know the old hand pumps? Hold on. Have you ever seen, not that I'm saying you should buy one, but if you've ever seen, let's see, make sure you're seeing this. You are. You ever seen the pumps like this? Or if we go back, you go to the forest preserve in Chicagoland, you'll see these hand pumps. I remember as a child going there with my parents, and you go like this, and oh, it stinks at first. Well, what makes it stink is the hydrogen sulfide in that water. Why it's there, I don't know. Never thought about that. I'll have to look it up. All right, let's get back to work. So what are we trying to find? How many grams H2S? What are we given? We have 3.1 times 10 to the 7th moles of H2S. And now I'm going to let you have some fun. What units would go over there in your answer? Your turn. Time's up. Well, we figured it out right here. We want grams of H2S. Now, if we had a magic ratio, it's not a magic ratio, it's chemistry. What units go on top and bottom of that ratio? Your turn. Giving everybody time to figure out what goes on top and bottom of that ratio. All right, how do you figure that out? Use your good buddy, your good friend, unit analysis. And how do you do that? Whatever you're trying to get to, the units go on top. Whatever you're trying to get rid of, the units go underneath. And now I'm going to write that in. And where do we find a relationship between grams of a molecule and moles of a molecule? Important information, test number 2. 1 mole of a compound equals the molecular weight of that compound. And the molecular weight of that compound is the sum of all atomic weights. So 1 mole of a compound equals the molecular weight of the compound. Oh no, we weren't given that. We have to figure out the molecular weight of hydrogen sulfide, the stinky stuff. How do you do that? Well, there's 2 hydrogen and 1 sulfur. So now I need to find the atomic weight, the 3 significant figures of hydrogen and sulfur. And if you look at hydrogen, 1.008 rounds off to 1.01. Sulfur, 32.066. I'm going to let you have time, your turn first, and I'll do that. Round that off to 3 significant figures. I'm looking at the clock and seeing how many seconds go by before I say it's my turn. Time's up. How do you round 32.066 to 3 significant figures? Keep the 3, keep the 2. Anything past the decimal is significant, also has zeros confined in between 2 numbers. So that's significant. The number to round off is 6. Is that 5 or higher or 4 or lower? I like the fancy signals here. And Humor Monday. But anyways, it's 6 is 5 or higher. So I drop that 6, the next 6, and the number in front, 0, I increase by 1, 32.1. So the sum of all atomic weights, I'll add this up. I get this. Now, remember, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures you're adding to the right of the decimal. This has 2, this has 1. So now I have to round this number off to one significant figure to the right of the decimal. Keep the 1, use the 2 to round off. That's 4 or less. Therefore, this is 34.1. Now, before I pick up my calculator, I said before, yeah, left hand. Moles divided by moles. Remember, anything divided by itself equals the number 1. Cancels out. That cancels out. What units am I left with? Grams of hydrogen sulfide, which is what I want. So now I can pick up my calculator, clear it, 3.1 times, oops, that's not what I want, 3.1, second key, double E, 7 now times 34.1, and my calculator gives me this number. And remember, when you're multiplying, dividing, you get the same number of significant figures in your answer as the number that has the fewest significant figures in what you're multiplying, dividing. This has 1, 2 significant figures. This 1 is an exact number. 34.1 is 3 significant figures. So you get the same number of significant figures in your answer as the number that has the fewest significant figures. And hopefully all agree 2 is smaller than 3. So round this number to 2 significant figures. I'm going to let you try that first. Your turn. All right. Round this off to 2 significant figures. Keep the 1, keep the 0. Use this to round off. So have 4 or less or 5 or higher, and 5 or higher. Drop that, increase that by 1. And this is your answer, 1.1 times 10 to the 9 grams of H2S. Stinky stuff, but still, that's how. Let's go through this again. How many grams H2S, hydrogen sulfide, are on 3.1 times 10 to the 7th moles of hydrogen sulfide? Figure out, what are you trying to find? Grams of hydrogen sulfide. What are you given? This is the only number we can start with. Figure out, what units do you want to get your answer in? Well, we did that. So here's that. If you had a ratio, it could take you from here to here. How would you figure that out? Use your good buddy, your good friend, unit analysis, and hopefully it is. It's been mine for a long, long time. And whatever you're trying to get to, the units go on top of the ratio. Whatever you're trying to get rid of, the units go underneath the ratio. And where do we get these numbers? 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of a compound is the sum of all atomic weights in that compound. So we need to find the molecular weight of hydrogen sulfide. 2 hydrogens, 1 sulfur. You get the atomic weight, round it off to 3 significant figures, do the multiplication, add it up, get the correct number of significant figures. Remember, when you add, you get the same number of significant figures to the right of the decimal point. And 2.02 has 2, 32.1 has 1. You add it up, you round it off, and it's 34.1 and 1. And now you can do the math because the units cancel out, and here's our answer. Now, important piece of advice from me, Dr. White, to you. On test 2, and actually all my tests in the final, but test 2, for this type of problem, if you were to put down the answer and it was wrong, you get 0 points. If you show me your work like this, and you make a math error, you get 1 point taken off and get most of the points. If you make a mistake like add this wrong, oh, that's a math error, you'll still get most of the points. It pays to show your work. Please do. Now, we've done these calculations already. All these different converting moles of an element to grams, converting moles of a compound to grams, converting grams of an element to moles, and converting grams of a compound to moles. We've done that today and last week. So you can go back and look at the video for when I did that on my whiteboard. Now, there's a principle called conservation of mass. And the law of conservation of mass is in any chemical reaction, the total amount of matter in the reactants is equal to the total, the T fell off, total amount of matter in the products. So whatever you start with, the total amount of matter in the reactants, remember, A and B are the reactants. C and D are the products of this chemical reaction that we show with the chemical equation. Now, sometimes I'll call this starting material. But the total mass you start with has to equal the total mass you end up with. Now, I'll never ask on a test, what's the law of conservation of mass? No, switch was off for that definition. But it's important to know, to understand the following. What I'm about to talk and tell you and teach you is probably one of the most important concepts in all of chemistry for me. What I'm going to teach you is really important to Dr. White, and that is the coefficients in a balanced chemical equation give the numerical relationship among the formula units consumed, used up, or produced in a chemical reaction. Now, better way of saying that, and this is really important, the coefficients in an equation give fixed molar ratios between substances consumed meaning the starting materials reacting and or produced in a chemical reaction. And know this. I'm never going to ask you to find it, but you should know how to use this. The coefficient in a chemical equation give the fixed molar ratio between, I could have written here, the reactants and the products in a chemical reaction. I think I'll change that. I like this better. The coefficients in a chemical equation give the fixed molar ratios between the reactants and the products in a chemical reaction. And what does that mean? Well, it's practice time. That's not what I wanted. That's not what I wanted. That's what I wanted. Let's look at a balanced chemical equation. And here we have a chemical equation. And what do we have? Oops, a mistake. Now it's correct. Two hydrogens react with one oxygen to make two water molecules. Now the coefficients are the number in front of the formula. When there's no number, that means it's number one. And here's probably the most important thing, one of the most important things I know in all of chemistry. What this really means is 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. Again, the coefficients, the number in front, give you molar ratios for a balanced chemical equation. And that's a molar ratios relationship. This tells you 2 moles of hydrogen. When there's no number, it's the number one. React with 1 mole of oxygen to make 2 moles of water. And this you can use. How? Let's look at the following problem. And let's look at the following. I'm not going to put points on this because you're going to see later today or tomorrow. This is part of a bigger problem. 10 points. Yep, 10 points. But let's look at this one. So how many moles of oxygen? One reacted. And let me put it here so you can see it. One reacted with an excess of, oops, made a mistake. Don't look. You can look now. With an excess of hydrogen gas to make 5.66 moles of water. So what are we trying to find? Moles of water. Nope. Moles of oxygen. What are we given? This amount of water. We're also told when reacted with an excess of one of the reactants. When you say excess of one of the reactants, that means you can ignore it, forget about it. So, how do we proceed? Well, first of all, another thing you will be given is the balanced chemical equation. So, how do we proceed? Well, there's only one number we have to start with, this. And if I had a ratio, what units do I want my answer? Moles of oxygen. And now guess what? Yes, it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. And I'll write those in. And so, where do I find a relationship between moles of oxygen and moles of water? From my balanced chemical equation, 1 mole of oxygen makes 2 moles of water. That's because the coefficients, the number in front of a balanced chemical equation, gives you molar ratios. So what this tells me is for every 1 mole of oxygen, I make 2 moles of water. Now, if we notice, moles of water divided by moles of water cancel out. Now, I'll pick up my calculator, clear it. 5.66 times 1 divided by 2. And my calculator gives me this. Now, this is very important. The coefficients, which are these numbers in a balanced chemical equation, are exact numbers. The coefficients in a chemical equation, which is where I got 1 and 2, are exact numbers. They play no role in how many significant figures. This has 3 significant figures. Our answer has 3 significant figures. I'm done. If I can spell. Now, 10 to the 0 is 1. You could also rewrite it. Either way is correct. And that's your answer. Now, let's go through this again. How many moles of oxygen, when reacted with an excess of hydrogen, is needed? Oh, forgot to write that in, sorry, is needed to make 5.66 moles of water. So we're trying to find moles of oxygen. Whenever you see something in excess, you can ignore it. I like that. I did. I must have some water. This is thirsty work. And now we have this. We start with the only number we have. We're trying to get the moles of oxygen, use unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get a relationship between moles of oxygen and moles of water? The balanced chemical equation tells you molar relationships. 2 moles of hydrogen, but because we're in excess, I can just ignore it. But 1 mole of oxygen makes 2 moles of water. 1 mole of oxygen, that's where I got the 1, makes 2 moles of water. Units cancel out, and there's my answer. And this is one of the most important concepts I know personally in all of chemistry. This is so powerful, and later today or tomorrow, you'll learn how powerful this is. But if I look at the clock, it's time for a break. I'll see you in about about 5 minutes, because I'm going to get up and stretch. Oh, I got the hiccup. I'm going to get up and stretch. Hopefully get rid of my burp or hiccups. See you in 5. Let's get started. Hi. For the break, I was talking about one of the most important concepts that I know in chemistry, and that's the coefficients, the number in front of a formula in a chemical equation give fixed molar ratios between reactants and products in a chemical reaction. And this is a key skill you should know. So hint, you should know this. And let's do another problem. All right, let's look at the following. Notice I'm not putting any points here because you'll see this is an important part of another problem which we should get to today or tomorrow. How many grams of ammonia NH3 is ammonia are made when you react 4.631 times 10 square grams of hydrogen with an excess of nitrogen? So first of all, let's talk about this reaction. A little background information. You don't need this for the problem, but I'd like to bring it up. This is a way of making ammonia in a chemical plant. And for many, many years, scientists were trying to make this work at what's called a high yield. When you react two things together, you make a lot of it, a high percentage. If you don't, it's not economically feasible. Well, it turned out two German chemists figured out a way to make this in high yield. This class, I won't be able to go into the specifics, but it's called the Haber-Bosch process. And it's probably one of the most important, as they say here, industrial chemical reactions ever developed. Why is this so important? Why is this little reaction? You're just taking hydrogen and nitrogen and reacting it to make ammonia, tiny little molecule. Why is this so important? Here's why. Once, and this happened about, we're talking about 1910, 1905, 1910, 1912, when Haber and Bosch came up with their solution or process. By making more ammonia, you can now make an inexpensive fertilizer. And because you could now make inexpensive fertilizer, farmers throughout the world especially in the United States, could grow a lot more food per acre. Again, because you could now make ammonia. Cheap ammonia allowed farmers to make a lot more food because they had cheap fertilizer, especially in the United States. Because we had more food in the world, guess what? This allowed the population of our planet to grow. That's an important outcome. Now, when you have chemical reactions like this to make products like ammonia, sometimes there's very good things. At the same time, sometimes not so good things. And this allowed cheap ammonia, inexpensive ammonia to be made in large quantities. So now there was inexpensive fertilizer that allowed farmers to grow a lot more food. Why? At the same time, ammonia being available inexpensively allowed for the, are you ready for this? The manufacture of a lot more and lower cost gunpowder and explosives. Now that there was an inexpensive way to make a lot of ammonia, you could make a lot more gunpowder and explosives, which means wars were cheaper to fight and could last longer, like World War I, World War II, the Korean War, Vietnam War, and a lot of other things going on since then on our planet. So there's good and bad. That's life. All right, let's get back to our problem. How many grams of ammonia are made when you react 4.631 times 10 to the 2 G is for grams hydrogen? Oops, I made a mistake. I got ahead of myself. All right. Sorry about that. It should be moles. This should be moles. Sorry about that. How many moles of ammonia are made when you have 4.361 times 10 to the 2 moles of hydrogen with an excess of nitrogen? Well, as soon as you say excess of a reactant, remember, these are your reactants. This is your product. You can forget about the nitrogen. I will. I like those hand signals. I forgot about you. All right, let's do this stepwise. Your turn. What are you being asked to find? What are you given? Remember, you're trying to find out what are you being asked to find? What are you given? All right. What are you being asked to find? How many moles of ammonia? What are you given? How many moles of hydrogen gas? You're also given this balanced chemical equation. That will be given to you in the problem. You need it. All right, we only have this number. I almost did it again. I got grams on the brain. No, it's moles of hydrogen. What are you trying to get to unit-wise? Your turn. And for those of you watching the video, you can put pause to figure it out. You need more time. All right, this is what we're trying to get to. Moles of ammonia. We had a ratio. What goes on top and bottom of that ratio? Units. Your turn. All right. How do we proceed to find out what units go on top and bottom of this ratio here and here? Use your good friend, your good buddy, unit analysis. And what we're trying to get to, the units go on top of the ratio. What we're trying to get rid of, the units go underneath. So I'll write them in. And where do we get those numbers? From the balanced chemical equation. Remember, wrong button, right button. The coefficients in a chemical equation give the fixed molar ratios, number of moles, between reactants and products in a chemical equation or reaction. So if we look up here, this tells me 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia. Remember, when there's no coefficient, it's the number 1. But since we have nitrogen in excess, we just ignore it, and I will. So, how many moles of ammonia? 2. How many moles of hydrogen are needed to make 2 moles of ammonia? 3. Again, you get these numbers from the coefficient, the number in front of the formula of a balanced chemical equation. The 2 comes from the 2 moles of ammonia. The 3 moles of hydrogen comes from here. Now, before I pick up my calculator, moles of hydrogen divided by moles of hydrogen cancel out, because anything divided by itself equals number 1 cancels out. I'm left with the right number. Now, I'm going to pick up my calculator, clear it. Multiply 4.631 times 10 squared times 2. Divide that by 3. And my calculator gives me this number. That 3.0873333333. Actually, they have a few more threes, but I didn't write them all down. Now, whenever you're doing a multiplication division, you get the same number of significant figures in your answer as the answer you get, or the number that you multiply and divide by, that has the fewest significant figures. Let me run that by again. When you multiply and divide, you get the same number of significant figures in your answer as the number you're multiplying and dividing that has the fewest significant figures. Well, this number has 1, 2, 3, 4 significant figures. The coefficients of a balanced chemical equation are exact numbers. Therefore, 2 is an exact number. 3 is an exact number, and they don't play a role in your final answer. Therefore, the only number you have to determine how many exact numbers will have significant figures in your number is 4. So I'll let you round this off to 4 significant figures. Your turn. Time's up. Keep the 3, keep the 0, keep the 8, keep the 7. Those are my 4 significant figures. Use the 3 to round off. Is that 4 or less or 5 or higher? And hopefully I'll pick 4 or less. I drop all this. And the correct number is this, 3.07 or 87 times 10 squared moles of ammonia. Remember, the key to this is the coefficients of a balanced chemical equation give fixed molar ratios between the reactants and products. Oh, let's do another one. And for this balanced equation, C3H8 is propane. That's the stuff you use for your barbecue. So let's look at this problem. How many moles of water are made when you react 8.11 times 10 to the fourth moles of oxygen with an excess of C3H8, which is propane? That's the stuff your barbecue. This is a reaction called combustion, and that's how you cook with propane in your barbecue, because you also get heat here, but we don't put that down. And for this problem, you're given that balanced chemical equation. You need it. So let's do this stepwise. What are you being asked to find? What are you given? Your turn. All right, time's up. What are we trying to find? How many moles of water? What are we given? 8.11 times 10 to the fourth moles of oxygen. Now, as soon as you see an excess of something, you can forget about it. I like that. I forgot about propane now. So we now have this. The only number we have to start with is this. We have some ratio. I'm helping you out. What units do we want our answer to be in? Your turn. Time's up. Ooh, my buzzer was broken. Time's up. It's right here. We want to get moles of water. And now I'll let you figure out what units go on top and bottom of that ratio. Am I patient or what? Don't answer that. All right, let's proceed. It's time to use your good buddy, your good friend, unit analysis. You'll find on test 2, it is your good friend, your good buddy. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And I'll write those units. So we want a relationship between moles of water and moles of oxygen. And where do you go with these numbers? Your turn, bud. Hint. Hint. Look there. Again, what numbers go in moles of oxygen, moles of water? Again, what number goes in moles of water, moles of oxygen? Your turn. All right, my turn. Where do you get these numbers? You remember. The coefficients in a chemical equation give the fixed molar ratios between reactants and products in a chemical reaction. And as it says up here, hint, know this, really, hint, know this. So we look at this balanced chemical equation. What it tells us is 1 mole of propane, which we can ignore because there's excess. Remember, when there's no coefficient, it's the number 1. But here we have 5 moles of oxygen. Remember, the coefficient, the number in front, gives you moles of that product or reactant. And this makes 3 moles of CO2, carbon dioxide, but we're not dealing with that. But we make 4 moles of water. So for every 4 moles of water, we need 5 moles of oxygen. Again, for every 4 moles of water, which we got from here, we need 5 moles of oxygen, which we got there. And now, before I pick up my calculator, remember, anything divided by itself equals number 1, cancels out. Moles of oxygen divided by moles of oxygen cancel out. I'm left with moles of water. That's what we want. Yay. So now I'll pick up my calculator, clear it. 8.11 times 10 to the 4th times 4 divided by 5. And my calculator gives me this answer. Remember, on test 2, underneath your name, it will say, please use proper significant figures for all calculated answers. I'm going to help you out, but you're going to have to learn how to do this on your own. You should have for test 1. This is 3 significant figures. This is an exact number. This is an exact number. Remember, coefficients of a chemical equation are exact numbers. Now, I'm going to let you figure out first, and then I'll do it. How many significant figures should your answer be? And write it down. Your turn. All right. Remember, the multiplication division, you get the same number of significant figures as in your answer as the number you're multiplying or dividing by that has the fewest significant figures. Well, exact numbers do not play a role. The only number you've used to figure out significant figures is this one, 3 significant figures. So your answer should have 3 significant figures. Oh, I'm sorry, got the hiccups. 6, 4, 8. Use this to round off. 4 or less, 5 or higher, and 5 or higher, increase that by 1. So the answer is 6.49 times 10 to the 5th moles of water. Let's go through this again. How many moles of water are made when you react 8.11 times 10 to the 4th moles of oxygen, O2, with an excess of C3H8 propane? And you're given this balanced chemical equation. Now, what are we being asked to find? Moles of water. What are we given? Moles of oxygen. This is the only number we have to start with, moles of oxygen, 8.11 times 10 to the 4th. We know we're trying to get the moles of water. How so? Because we figured that out here. And you use your good buddy, your good friend, unit analysis. I was thinking of picking up the whistle, but I don't want to give you whistle overdose today. Moles of water goes on top. Moles of oxygen go underneath. Where do we get these numbers? Where do you find the relationship between moles of a compound, a reactant, and moles of a product in a balanced chemical equation? And you get that by the coefficients. The coefficients, hint, know this. Yep, stuff I just outlined or highlighted. The coefficients in a chemical equation give the fixed molar ratios between reactants and products in a chemical reaction. And here, chemical reaction, 1 mole of propane reacts with 5 moles of oxygen. The coefficient 5 tells you it's 5 moles to make 3 moles of CO2. The 3 tells you 3 moles of that. And the 4 tells you you make 4 moles of water. So we get the 4 moles of water from here. We get the 5 moles of oxygen from here. Notice the units cancel out. You're left with moles of water. Do the math, proper significant figures, and we're done. That's it. You should practice this. This is one of the more difficult concepts students have. Now, I'm going to end a little earlier today because the next concept I want to tie this all together with takes a lot of time. I don't want to rush it. So we're going to end a couple minutes early today. Don't tell anybody I'm doing that. Shh. But let me remind you, 1, tomorrow the density lab is due. Hand in your labs. They're 10 points per lab. Make sure when you hand in a lab, it's in a single PDF file. When you hand in a lab, make sure it's a single PDF file, but your selfie, you with take a picture of something from that lab, you should also include, otherwise you'll get 0 points. Oh, by the way, I'm caught up with labs. I got to see your selfies. I got to find out I'm dealing with real people. Great pictures. Thank you. Now, don't forget, tomorrow I have my office hour, Tuesday from 6 to 7:15. You have any questions, any problems, stop by and see me. It's on Zoom. You don't even have to get in your car and come to COD. And with that, I'm done for today. I'm going to say, Gang gesund. Goodbye. I'll see you tomorrow. Bye now.